All right, so far I've been talking in a little bit of generality about what we're made of. And this is the punchline for the halfway point of the talk. You're all made of quantum fields, and I don't understand them. At least I don't understand them as well as I think I should. So what I want to do now is go into a little bit more specifics. I want to tell you exactly what quantum fields you're all made of. In fact, I'll tell you exactly what quantum fields exist in the universe. And the good news is there's not many of them. So I'll simply tell you all of them. So we started with the periodic table. This is the new periodic table. And it's much simpler. It's much less. There are the three particles that we're all made of. There's the electron and the two quarks, the up quark and the down quark. And as I've stressed, the particles aren't fundamental. What's really fundamental is the field that underlies them. And then it turns out there's a fourth particle that I've not discussed so far. It's called the neutrino. It's not important in what we're made of, but it does play another important role in elsewhere in the universe. These neutrinos are everywhere. You've never noticed them, but since I began this talk, something like 10 to the 14 of them have streamed through the body of each and every one of you. As many coming from above, from outer space, as actually coming from below, because they stream all the way through the Earth and then keep going. They're not very sociable. They don't interact. So this is what everything is made of. These are the four particles that form the bedrock of our universe. Except then something rather strange happened. For a reason that we do not understand at all, nature has chosen to take these four particles and reproduce them twice over. So this is actually the list of all the fields that make up particles in our universe. So what are we looking at here? This is the electron. It turns out there are two other particles which behave in every way exactly the same as the electron, except they're heavier. We call them the muon, which has a mass of something like 200 times the electron, and the tau particle, which is 3,000 times heavier than the electron. Why are they there? We have no idea at all. It's one of the mysteries of the universe. There's also two more neutrinos, so there are 3 neutrinos in total, and the 2 quarks that we first knew about are now joined by 4 others that we call the strange quark and the charmed quark, and then by the time we got here, we really ran out of any kind of inspiration for naming them. We call them the bottom quark and the top quark. So I should stress, we understand things very, very well going this way. We understand why they come in a group of 4. We understand why they have the properties that they do. We don't understand it at all going this way. We don't know why there's 3 of these rather than 2 of them, 17 of them. That's the issue. But this is everything. This is everything in the universe. Everything you're made of is these 3 at the top there. And it's only when you go to more exotic situations like particle colliding that we need the others on the bottom. But every single thing we've ever seen can be made out of these 12 fields. These 12 fields interact with each other, and they interact through 4 different forces. 2 of these are extremely familiar, the force of gravity and the force of electromagnetism. But there's also 2 other forces which operate only on small scales when they're nucleus. So there's a strong nuclear force which holds particles together like protons and neutrons. And there's a weak nuclear force which is responsible for radioactive decay, among other things that make sunshine. These forces is associated with the field. So Faraday talks about the electromagnetic field, but there's a field associated with this, which is called the Coulomb field, and a field associated with this, which is called the boson. There's also a field associated to gravity. And this was really Einstein's great insight into the world. The field associated with gravity turns out to be space and time itself. So if you've never heard that before, that was the world's shortest introduction to general relativity. And I'm not going to say anything else about it. I'll just let you figure that one out for yourself. Okay, so this is the universe we live in. There are 12 fields that give matter. I'll call them matter fields, and 4 other fields that are the forces. And the world we live in is this combination of the 16 fields all interacting together in interesting ways. So this is what you should think of the universe as like. It's filled with these fields, fluid-like substances. 12 matter, 4 forces. One of the matter fields starts to oscillate and ripple. Say the electron field starts to wave up and down because there's electrons there. That will kick off one of the other fields. It will kick off, say, the electromagnetic field, which in turn will also oscillate and ripple. There'll be light, which is electron. So that will oscillate and ripple. At some point, it'll start interacting with the quark field, which in turn will oscillate and ripple. And the picture we end up with is this harmonious dance between all of these fields, interlocking each other, swaying, moving this way and that way. That's the picture that we have of the fundamental laws of physics. We have a theory which underlies all this. It is, to put it simply, the pinnacle of science. It's the greatest theory we've ever come up with. We've given it the most astonishingly rubbish name you've ever heard of. We call it the Standard Model. Okay? When you hear the name the Standard Model, it sounds tedious and mundane. It should really be replaced for the greatest theory in the history of human civilization. Okay? That's what we're looking at. Okay, so this is everything, except it's not quite. I've actually just missed out one field. There's one extra thing we know about, which became quite famous in recent years. It was a field that was first suggested in the 1960s by a Scottish physicist called Peter Higgs. And it was, by the 1970s, it had become an integral part of the way we thought about the universe. But for the longest time, we didn't have direct experimental evidence that this existed, where direct experimental evidence means we make this Higgs field ripple, so we see a particle that's associated to it. And this changed. This changed famously 4 years ago at the LHC. These are the two experiments at the LHC that discovered it. They're sort of the size of cathedrals and just packed full of electronics. They're astonishing things. This is called ATLAS. This is called CMS. The Higgs particle doesn't last for long. The Higgs particle lasts about 10 to the minus 22 seconds. So it's not like you see it and you get to take a picture of it and put it on Instagram. It's a little more subtle. So this is the data, and this little bump here is how we know that this Higgs particle existed. This is a picture of Peter Higgs being found. So this was the final building block. It was important. It was a really big deal, and it was important for two reasons. The first is that this is what's responsible for what we call mass in the universe. So the properties of all the particles, things like electric charge and mass, are really a statement about how their fields interact with other fields. So the property that we call electric charge of an electron is a statement about how the electron field interacts with the electromagnetic field. And the property of its mass is the statement about how it interacts with the Higgs field. So understanding this was really what was needed so that we understand the meaning of mass in the universe. So it was a big deal. The other reason that it was a big deal is this was the final piece of our jigsaw. We had this theory that we called the Standard Model. We've had it since the 1970s. This was the final thing that we needed to discover to be sure that this theory is correct. And the astonishing thing is, this particle was predicted in the 1960s. 50 years we've been waiting. We finally created it in CERN. It behaves in exactly the way that we thought. Absolutely perfectly behaves as we predicted using these things.